Welcome, class, and a very good morning to all of you. Today, we will be discussing about or those things which basically is an integral part of chemistry. We have started our journey of chemistry long back, and we have discussed, we have understood, we have learned many things which are related to chemistry. But today, we are now going to discuss and now going to step in to the world which actually forms the fundamentals, the basics, or the basics in terms of the core section of chemistry. This chapter is a very important, very interesting, because the knowledge of this chapter after a certain point of time will actually develop the interest about the subject, actually develops the fun which is going on with the subject. So, this chapter reveals and unleashes many questions, many answers to a, what should I say, a very thinkable mind. And for those who doesn't think also in terms of chemistry, they also start thinking in terms of chemistry. So let's begin. It was it was basically during that when I'm talking about this time about a long time back, 6th century BC. During that time, a person, he was once a day, one in a day, rather one day, he was having his food, and he was very in a relaxed mood, cherishable mood, and he was enjoying the food slowly and with time going by. But nobody knows suddenly what happened. He started thinking of something which nobody during that time have ever thought of. So nobody had thought of those things. But it came to his mind. But how it came to his mind, still it's an unanswered question. It came. He realized that since while he was having the food, he was chewing, and and within his hand also he was making something, rather scratching or pasting a different sort of thing to make the food into a different state, from the solid into a paste structure, paste like thing. So that particular incident struck his mind that he was basically unable to break the food after a certain point of time. Though he was sure that he can feel the particles, he was able to feel the food particles, he can see that one. While chewing, he was able to chew that one into much, much smaller pieces. But there is a limitation to his capability, and thus he was not being able to break that one after a certain point of time. Since the food was solid, he was he was though convinced that, okay, it's possible that this is his limitation, but there is also a possibility that this particular solid substance is not, or rather cannot be broken into much smaller after a certain point of time. If that is the limitation with with the food of what he is having, then the liquid which he was drinking, that also should be breakable, but also definitely after a certain point of time will become unbreakable. So I cannot break. So he started to think that there is a limitation of mine, as well as for the humans, that after a certain point of time, nothing can be broken. And that particular concept led to the foundation of the concept of matter. And this concept of matter actually led him to come up led him to come up with a new terminology. That is, that he termed the smallest particle, which he was not being able to break into, rather he was not able to reach to that particular, which he is, according to him, that after a certain point of time, there nothing can be broken into much finer or much smaller. So he termed those particles, whichever of whatever the substance is, irrespective of the substance, that after a certain point of time, since it cannot be broken down, those particles he termed as anu. It's basically a Sanskrit word. The term anu. And he termed that word, that oral particles, as anu. Now, this concept of matter, this was basically a very general idea and a foundation stone of the modern scientific and the theories which are having, the researches which are going on right now. But this, during 6th century BC, this was a very, very revolutionary theory. But it was not so much popularized during that time. It was accepted, but not fully, because complete evidences were not there, and it was actually a theory, was nothing else. But later, this theory only led the foundation or became the backbone of the theory of atoms. So the concept of atoms came up with the concept of matter, and whatever the theory which this person gave during 6th century BC as anu, it was basically, as I said, a Sanskrit word. The concept of atoms came into existence, which was basically later when it came as a scientific reference, of course. Now, those things came up as a much later, thousands of years later, and that was then accepted, and which proved that the 6th century BC theory of anu was actually correct. The person, you might be very happy to know that this person was basically none other than was an Indian philosopher, Maharshi Kanat. So he was the person who actually came up with this idea of anu. All right. Now this theory, or his theory, was later in that this was basically, I'm talking about the 6th century BC. But after almost 100 years or later, two Greek philosophers, basically Leucippus and Democritus, he also proved that one right, that the concept of anu and the concept of atoms are absolutely correct. And with this, I welcome you to the world of atomic structure. So let's step into the world of atomic structure. So as I was saying, as I was continuing with our discussion of the concept of anu, which was strengthened by the two Greek person of Leucippus and Democritus, who was basically a student of Leucippus. So it was basically around 370 or 460 BC, something like that, which was almost about 100 years later to the concept of anu came into existence. They also affirmed that yes, that concept was correct. The theory was not a false one. Thousands of years later, almost about two and a half thousand years later, 2,500 years later, or 2,000 years later, John Dalton, John Dalton in 1808, he came up with the theory of atoms. That means this concept of atoms, the existence of atoms, the structure of atoms. John Dalton didn't give the exact model for an atom, or how an atom how an atom looks like, not exactly looks like, rather how the structure of an atom is completely, but he gave a very clear concept, a clear idea about the structure. Rather, it was basically an overview about the structure of an atom. So he laid the foundation of this concept of atoms, which was basically a scientific theory concept containing the scientific evidences, followed by he led also his theory on the structure of atom. Now, structure of atom, regarding that, the first scientific theory, he had many explanations and many postulates regarding his atomic theory. What are they? The Dalton's atomic theory, the first point was matter consists of very small and indivisible particles called atoms. Now, this small and indivisible, so small we can understand by that concept itself, that since the concept was about that after a certain point of time, we cannot break anything, matter, solid, liquid, gas, or we cannot break anything much more further. Now, this theory was basically do not mix up. It was breakable, but this theory was there in the community, in the scientific world during the early 19th century, 1808. It's almost from now on. It's almost 200 years back. All right, almost 200 years back. So there is no point of considering that it was basically the indivisible particle. So matter consists of small, it was very small, and indivisible particles. According to Dalton, atoms cannot be broken down into much smaller substance, so they are the smallest. He also said that atoms can neither be created nor can be destroyed. Atoms can neither be created nor it can be destroyed. So atoms, we cannot produce atoms, neither we can create atoms. So this theory is basically for the human limitations, that atoms, we cannot produce atoms. We means the living system, we cannot produce atoms, especially the humans, we cannot produce atoms, or neither we cannot destroy atoms. So we cannot control the atoms. So that's the thing. Now, atoms of an element are all identical in nature. So far we are very much comfortable, and we know that what an element is, and we know that an element is made up of atoms, and they all are rather not particles. Rather, let's not go into atoms first. Elements are made up of particles, and all the particles are identical in nature. That means as if twins. So all the particles are identical in nature, twins rather, because they behave the same way, they looks like the same way, size, everything the same. So atoms of an element are identical in nature. Now, atoms of elements, when they combine in small numbers to form molecules. Small number to form molecules. Now, small numbers to form molecules, that means when they're forming molecules, atoms do not take up, it's not a molecule that it will have almost about a number of 100 or 150. They try to form molecules with small numbers, that means 1, 2, 3, 4, 5, 6, like that way. So these are small numbers. So it's not that they will have numbers as if they are having, the one molecule is having, when they're forming molecules, one molecule will be having, especially with an element, or maybe of 100 atoms. So 100 atoms of a particular element will combine to form one molecule. That's not the point. So atoms of elements, if they combine to form molecules, they can combine in small numbers to form molecules. But if this is considered for compounds, definitely there also the numbers slightly increase. But that is during there a new term comes into the new concept. That is, they will combine when it's for compounds in small ratios. Small ratios means and small ratios means that means it will be not only small. That means the value of the ratio. The ratio means the in what order, but it has to be. It cannot be in fraction. So it's not that 2.5 times or 2.5 parts of a particular element A will combine with 3.7 parts of B. So it's not like that. So neither decimals, neither fractions, it's not any sort of 1/7 or 2/3 or something like that. These sort of things are there. So they will come if the atoms are combining to form atoms of elements are combining to form molecules, then definitely molecules of compounds, and definitely they'll do in whole number. Definitely they'll do in whole number ratios. Okay, simple ratios have no whole number ratios. Now, moving on to another, that is, atoms are the smallest particle to take part in a chemical reaction. Now, since compounds are there, that definitely are a result of a chemical reaction. So Dalton was of the opinion that atoms are the smallest particle to take part in a chemical reaction. So when a reaction will take part, atoms are the only one who takes part in a reaction, nothing else, because they are the smallest. Since atoms are the smallest, and the reactions actually takes part in that particular order. So atoms are the smallest particle to take part in a reaction. That was his theory, his concept, or his proposal. These postulates basically, Dalton's actually was able to solve and able to answer, and following these postulates, many answers of many scientists around the world during that time was solved. The entire scientific community was very happy with the concepts and with the proposals and the theories of Dalton's atomic theory, and because many of their questions were answered following these particular postulates. But there came up a problem in for many years. The Dalton's atomic theory ruled the scientific community, but later, almost nearly 100 years later, the Dalton's atomic theory was rejected. It failed. Dalton's atomic theory actually failed. The question arises how. Now, if these were basically the molecular structures of how the molecule will look like, it is as we said, or as he said, that it will be two simple numbers, two small numbers to form molecules by the elements. You can see there are binary, there are ternary, there are quaternary. So it's one atom forming molecule, two atoms forming molecule, three atoms forming molecules, four atoms forming molecules, four means with quaternary. So you can over there you can see the sexternary. There is a six, or rather five and six, and previous to that it's a pentenary, quaternary, then septenary, seven atoms to form one molecule. So these many proposals, though it led to the and though it resolved the problems of many questions which arose during that time, but there was a problem, and that was later, as I said, was with the discovery of those new evidences related to the atomic structure. Dalton's atomic theory failed. It failed. Now, why it failed? It failed because it in the year 1897. It was basically in the year 1897 when a fantastic person named Sir J. Thomson, he discovered something. He discovered that he discovered some new particles which have no connection with the normal or with a general atom, with the properties of an atom. The properties of those particles were no longer similar to the properties of the atoms. Now, he named that one as that J.J. Thomson named that one as electrons. He was basically sure because these are not atoms because since the properties are no way similar, and secondly, it was emitting out from those particular substance of his experiment. So if the point was if atoms are the smallest, then atoms would have come out. But since the results are something different, these particles are oozing out from the substance. Hence, these particles are different, and he named these particles as electrons. Now, followed by Sir J.J. Thomson, another concept was first came into existence before this electrons was discovered. The concept was regarding some other particles. It was given by Sir Eugen Goldstein, which was later confirmed by Sir Ernest Rutherford in the year 1911. And they proposed and they discovered rather uh, another set of particles, and they named as protons. And basically, both of them observed, and they basically, Rutherford observed that protons are behaving differently. Rather, not differently means not a difference in one particular sense. Different means just opposite sense. So protons are basically behaving in just in an opposite manner in comparison to that of the electrons. So now, after even Goldstein and Rutherford have given the proposal, or rather about the discovery about electrons and protons, few years later, another famous person, Sir James Chadwick, that he discovered in 1932 another particle with respect to that of an atom. It was neutrons. It was neutrons. Now, so many particles actually proved Dalton's theory incorrect, and that led to the failure of the Dalton's atomic theory. The first, of course, the point of failure was it does not account for the subatomic particles, of course. The second, it does not account for the isotopes. So definitely, if you know what isotopes, it's okay. But after a few more classes, you will come across the word isotopes. What isotopes are? It also isotopes are basically different form or different same elements but existing in a different way. The same another point. The same thing happened with the existence of allotropes because the Dalton's theory was not explaining about isotopes neither for the allotropes. So these things, one of the major drawback was the subatomic particles, followed by these, so it led to the failure of the Dalton's atomic theory. So after the Dalton's atomic theory failed, Rutherford came up with a new theory, that is regarding the structure of an atom, and he proposed the atomic model, known as the Rutherford's atomic model. The Rutherford's atomic model came up in 1911, and he proposed that atoms are set in the if you are able to break atoms, then at the center of an atom you will get a positively charged component, that is the central positive charge. That means at the center there is a positive charge density, definitely with the protons, and the electrons, which are actually negatively charged, they are revolving around the nucleus in fixed paths, and those fixed paths are known as orbits, and within those orbits the electrons are rotating around the nucleus. So the central part is the central positive charge, having the protons called the nucleus, and the electrons are revolving around the nucleus in fixed path known as orbits. So with this concept, Rutherford was able to convince the scientific community, and this model was accepted. Though this model also failed after a certain point of time, but during 1911 this model was accepted. Now, today's class, I'll just going to wind it up for today's class. But before winding up, I will definitely want you all to watch this video, which is basically a overview, a quick recap of what we have studied so far. So, okay.
The laws of chemical combinations created ripples in the stagnant pool of chemistry. They enabled scientists to carry out various experiments that helped in forming strong foundations in chemistry. However, the laws still needed experimental evidences and proofs. Only then would they be accepted. It was around the first decade of the 19th century that a chemist and a physicist from England named John Dalton was successful in answering many questions. He proposed a theory which was then known as the Dalton's atomic theory. With this theory, many concepts regarding matter, composition of matter, atoms, and even combinations of atoms resulting in compounds were better understood. Okay, let's first take a very quick look at the 6 major postulates of his theory. First, he said that all matter is made up of very tiny particles called atoms. Secondly, he suggested that atoms are indivisible particles which cannot be created or destroyed in a chemical reaction. Third postulate was, atoms of a given element are identical in mass and chemical properties. Similarly, fourth postulate was that atoms of different elements have different masses and chemical properties. Fifth postulate stated that atoms combine in a ratio of small whole numbers to form compounds. And lastly, the relative number and kinds of atoms are constant in a given compound. I know I just rattled off the postulates. Don't worry, let us now understand each postulate one by taking the same example of elements A and B giving rise to compound C. The first point stated that all matter is made up of very tiny particles called atoms. It means that when we go on dividing matter into smaller and smaller sections, what we get at the end is atoms. So can we say that elements A and B are made up of atoms? Yes, in fact, compound C is also made up of atoms that have combined together. So the first postulate was very easy to understand. The second postulate was that atoms are indivisible particles which cannot be created or destroyed in a chemical reaction. Now, what do we mean by this? Yes, it means that atoms are like the fundamental units. Dividing them further is not possible. Also, in a chemical reaction, atoms may combine together to form new units. However, no new atoms can be created and existing ones cannot be destroyed. So in this case, the atoms of element A and B are just combining to form compound C. So can we say that no new atoms are formed in this case? Yes, and similarly, no atom is destroyed. Let's move on to the third one now. The third postulate states that atoms of a given element are identical in mass and chemical properties. If we zoom into the element A, we find all the atoms that make up element A are just the same. And in what sense are these same? The atoms have identical mass as well as chemical properties. In simple words, the third postulate states that all atoms of a given element are identical. And does this explain the fourth postulate too? Yes. The fourth postulate states that atoms of different elements have different masses and chemical properties. So are we able to notice that atoms in element A are different from those in element B? Absolutely. And in what sense are they different? Atoms in element A and B have different masses and even different chemical properties. In simple words, it states that atoms of different elements are different. The fifth postulate states that atoms combine in a ratio of small whole numbers to form compounds. Now, what do we mean by this? In this chemical reaction, we find elements A and B reacting and giving us the compound C. If we observe well, a unit of compound C has 2 atoms of element A and 1 atom of element B, right? So aren't these whole numbers? Yes, this means that in any compound, the elements are always present in a ratio which comprises of whole numbers. You will not find half or 3/4 atom combining with the other. In case of water, we always have 2 hydrogen atoms and 1 oxygen atom combining to form 1 unit. In 1 unit of carbon dioxide, we have 1 carbon and 2 oxygen atoms. The same holds true for all compounds. The number of atoms of a particular element in a compound will always be a whole number. Now for the last one. The sixth postulate states that the relative number and kinds of atoms are constant in a given compound. The same explanation that compound C has 2 atoms of element A and 1 of element B makes us understand this. Yes, if we scan compound C, we will always find 2 atoms of element A and 1 atom of element B in a single unit. And this is applicable for all compounds. We've already looked at 2 examples, water and carbon dioxide. In case of 1 unit of water, we always have 2 hydrogen atoms and 1 oxygen atom. And in a single unit of carbon dioxide, we have 1 carbon and 2 oxygen atoms. Carbon monoxide has 1 atom of each, that is carbon and oxygen. While 1 unit of ammonia always has 1 nitrogen atom bound to 3 hydrogen atoms. So the number of atoms will always be constant in a unit of a particular compound. In a nutshell, all these postulates help chemists to further understand behaviors of elements and the compounds formed from them. But for understanding these elements and compounds, knowing the concept of atoms is necessary.
Doing, we'll be definitely doing in our next class. So till then, thank you so much. Stay at home and take a very good care of yourself. Thank you.